Okay, so singular value decomposition. Well, because of the word singular in this phrase, or SVD, because of the word singular, whatever this technique is, actually it sounds quite scary. And actually, that was also my feeling when I had my first exposure to it. But actually, once you know what it is, there's actually nothing singular about it. Usually in mathematics, singular means something is about to blow up to infinity, but clearly none of the numbers that we're going to be talking about is going to blow up. So in fact, I don't even understand why people who first made up this expression even chose to use such a horrific adjective to describe the technique. Well, it's I would say it's a generalized eigenvalue problem. At least that's how I would like to view this technique. So the eigenvalue problem really makes sense for a matrix which is a square. So it has to be an n by n, equal number of rows and columns. And to guarantee that all the eigenvalues are real, we also have to require that the hermiticity condition be satisfied for this matrix. But obviously, such a matrix is a rather special subset of all the possible matrices one can write down. Right? So A can be m by n rather than n by n. Okay, m and n need not be the same number. And when it's not the same size horizontally as vertically, of course, you cannot even think about the hermiticity of the matrix. And even when A is a square like m by n, it's not always the case that this matrix be Hermitian. Okay, so for non-Hermitian matrices, we don't even know whether we can define something like the eigenvalues, and if we did, whether the eigenvalue will be real. Does that mean that the entire idea of eigenvalue and eigenstates fail completely once we move away from the Hermitian condition of a matrix? Well, the answer is no. In fact, there's something like the eigenvalue, something like the eigenvector, even for matrices that are not Hermitian. And so in that sense, I want to call this entire technique a generalized eigenvalue problem. And I'm going to go through the decomposition techniques of singular value decomposition. And just to simplify the discussion, I'm going to assume that the matrix I have in mind is n by n, so it's a square matrix, but not necessarily Hermitian. If it's a square and Hermitian, then you don't really have to worry about singular value decomposition. The eigenvalue decomposition using the unitary matrix, which is something we already talked about, is going to do a perfectly good job. But when A is not a Hermitian matrix, there's no guarantee that a set of orthogonal eigenvectors will exist, there's no guarantee that the corresponding eigenvalues will be real. However, although A itself may not be Hermitian, A dagger A is Hermitian. Okay. Well, A dagger is just a Hermitian conjugate of the matrix A. And if you take the Hermitian conjugate of this entire thing, then it's A dagger multiplying A dagger dagger, which is A, so it's A dagger A. So comparing these two expressions, you can see that this is in fact a Hermitian matrix. Okay? So once we have a Hermitian matrix, we can apply all of the wonderful mathematical results that pertain to a Hermitian matrix, including the existence of a eigenstate. Okay, so this Hermitian matrix A dagger A acting on one of its eigenstates will give out some eigenvalue multiplied by the state itself. Okay, but instead of writing out the eigenvalue as Si, I wrote it as Si squared, implying that this eigenvalue has to be at least non-negative. It might be 0, but at least it cannot be a negative number. Okay, which is what allows me to write the eigenvalue as some number squared. Why is that? Well, the proof that the eigenvalue of A dagger A is always non-negative is extremely simple. So all you have to do is just take the overlap of this whole thing with the psi I to the left. Okay. However, if we define these new vector psi I prime as the A matrix acting on this eigenvector psi I, all right, then its conjugate psi I prime is this one, followed by an A dagger. Okay, so this whole thing is just an overlap of a psi I prime with a psi I, which has to be non-negative. Okay, so, sorry, prime. So either the A acting on these eigenvector vanishes entirely, in which case the corresponding eigenvalue will be 0. Or if it's not vanishing, then the corresponding eigenvalue necessarily has to be positive. Okay, so we have excuse me, nicely proven the non-negativity of the eigenvalue for the A dagger A. So A dagger A is sort of like the square of the matrix, which is kind of a quick way of seeing why its eigenvalues are always non-negative. So here's the thing, even though A itself is not Hermitian, we can still construct the set of eigenstates as obtained from not A, but A dagger A. Okay, and since at the beginning I said I will only concerning myself with a square matrix, both A and A dagger are n by n, and therefore there will be only n different eigenvectors, psi 1 through psi n. Okay, so these are the n eigenvectors. Now, if we have a n different eigenvectors that are mutually orthogonal, and these are the eigenvectors of some Hermitian matrix, we know that we can make a unitary matrix out of these vectors. Okay, so by stacking up these n different eigenvectors, we come out with some sort of unitary matrix, and I will call that V. Okay, and like any complete set of eigenvalues of a Hermitian matrix, they also satisfy this completeness relation. Okay, so we talked about this before in the context of diagonalizing a Hamiltonian, but here the role of a Hamiltonian matrix is being played by A dagger A. Sorry, A dagger A. Okay, so what do we do next? So what we do next is to decompose the A matrix into the various eigensectors of these A dagger A, and the way we do that is just multiplying A to its right by the sum of these projectors. Okay. And you can put this in this form, A psi I, psi I. Okay. And then you can also put this into this form. So A psi 1, A psi 2, etc., all the way up to A psi n. And here we have a row of the eigenvectors, psi 1, psi 2, psi n. Okay, so if you do a multiplication of this object with this object, pretending that each element is like a number, then you indeed arrive at these at this expression. Okay, but also notice that this object that appears as a big column is actually nothing but a Hermitian conjugate of V. Okay, so then we can write this whole thing as simply as V dagger showing up on the right. Okay, so A, the original matrix that we started, has this decomposition in terms of some sort of matrix multiplied by unitary matrix V dagger. Just remember that if V is unitary, then so is V dagger. Okay, but we're not entirely sure what this is. So instead of writing A psi 1, I'm gonna write phi 1, phi 2, all the way up to phi n times V dagger. And keep in mind that each phi I is is just A acting on a given eigenvector psi I. Okay, that's the definition of a phi I. Okay, so that's roughly 1/2 of the singular value decomposition. And now let's try to finish up the other 1/2 of the singular value decomposition. Okay, and the second half of the SVD relies on making sense out of these new object called phi I. Phi I, it turns out, is an eigenvector of a dagger. Let me prove it. The proof is really simple. Suppose A and A dagger. Oh, by the way, A and A dagger is also Hermitian. Okay. So when you have a non-Hermitian matrix A, there are two ways of making a Hermitian matrix out of it. Either by making A dagger A or by making an A dagger. So we already used the eigenvectors of A dagger A over here to construct a whole bunch of eigenvectors. And now we're going to think about the other possibility of constructing the Hermitian matrix, A dagger, and think about its eigenvectors. And the claim is that this new object that we defined and called phi I is precisely that eigenvector. Okay, so A dagger and phi I was what? It was A psi I. Okay, but you can group this whole thing in this way: A dagger A acting on psi I. Okay, but this is nothing but the definition of this eigenvector psi I. Okay, psi I was defined to be the eigenvector of A dagger A, which is Hermitian matrix. And the eigenvalue was worked out to be some non-negative number, like that. Okay, so the result of this operation is SI square times A psi I. But A psi I was, by definition, phi I. Okay, so then we have this relation A dagger acting on phi I equal to the same eigenvalue as before, multiplying the phi I state, which means that phi I is an eigenstate of the other Hermitian matrix, namely A dagger. Okay, well, so what did we find? What we found was that this A matrix has this mathematical decomposition into a whole collection of eigenvectors phi and the whole collection of eigenvectors psi. Remember, this V was built out of the eigenvectors of from eigenvectors of A. What was it? A dagger? Forgot. Yeah. So the V unitary matrix was constructed out of the eigenvectors of A dagger A. And now these phi are the eigenvectors of A dagger. Okay, that sounds pretty cool. That means any vector can be written sort of as a product of its one set of eigenvectors and the other set of eigenvectors. Sometimes these are known as the left eigenvector and the right eigenvector, but more precisely, these are the eigenvectors of A dagger and A dagger A. And whether you call them left eigenvectors or right eigenvectors is not particularly relevant. Okay, but there's a small problem with this decomposition. So the decomposition we have so far is that A can be decomposed as a phi 1, phi 2, all the way up to phi n, multiplied by psi 1, psi 2, etc., psi n. And this part was a unitary matrix, but unfortunately this part is not unitary. And the reason why this is not unitary is because these eigenstates are not normalized. Okay, so from the definition of phi I, well, phi I was just A acting on the psi I. And here we have its conjugate, so. All right. But A dagger A acting on psi I gives you SI square. And by definition, we assume that these psi's are already normalized. So we just have SI squared. Okay. So that means the overlap of the phi I eigenvector does not give you 1, but rather it gives you some SI square. So it's not normalized. And the only way to make a unitary matrix is just if you put together a bunch of normalized eigenvectors. And using the unnormalized eigenvectors like this, just putting them together like this is not going to produce a unitary matrix. Well, but there's a simple recipe to fix that. There's a simple fix. Well, instead of putting together these unnormalized eigenstate, I can put together properly normalized eigenstates. Okay, I just have to divide each eigenstate by the square root of its norm. So here we go. Okay, then this will be a properly normalized unitary matrix. Well, the only remaining trouble is that A has this decomposition, and then but the unitary matrix is not the previous expression, but has this various factors in front of each eigenstate. But if you think just for a little bit, then you realize that this is actually S1 inverse phi 1, S2 inverse phi 2, etc., Sn inverse phi n, multiplying S1, S2, etc., Sn. So what shows up here is a diagonal matrix whose diagonal elements are these singular values, but without the square. Okay, so if you take the product of this with that, then you get that. Okay, and this thing we called a U, and this thing is normally called the sigma for some reason. So then finally we obtain this decomposition of the A matrix as the product of one kind of unitary matrix multiplied by some sort of diagonal matrix multiplied by the other kind of unitary matrix. Okay, and this is the famous result of the SVD. And remember that when we had some sort of a Hermitian matrix, then the decomposition was in terms of some unitary matrix U dagger, and there is the H diagonal, and then there was U to its right. So so this is a unitary transformation of a Hermitian matrix, which brings the Hermitian matrix into its diagonal form. And that transformation required the use of these unitary matrix. And you can notice this similarity between the singular value decomposition and the unitary transformation. The difference is that one has to involve two different kinds of unitary matrices rather than a single one. And the other difference is that although there is a diagonal matrix that shows up in the middle, and there's a diagonal matrix that shows up in the middle, the eigenvalues of the Hermitian matrix can be any real number, both positive and negative. But the elements in this diagonal matrix can only be a non-negative number. Okay, so that's the key difference between the singular value decomposition and the diagonalization of a Hermitian matrix. But the fact that only the non-negative numbers can appear in this diagonal matrix can actually lead to some interesting consequences, one of which is the possibility to define something called the entanglement entropy. And I will come to this in my next video.